gentlemen, class recording has started. So, as I mentioned to you guys previously, the last section of Chapter 4 deals with projectile motion, or like it says up on the board, motion in 2 dimensions. And it starts with this demonstration that if you're watching the recording you can't see, but, so I take the baseball, and I throw it up in the air, and I catch it. Okay? Last chapter, Chapter 3, when we dealt with acceleration, we did this demonstration extensively, right? And we talked about how the gravity affects the motion of that object, slows it down on the way up, speeds it up on the way down. When it gets back to my hand, it's going just as fast as it was when I threw it, but now in the other direction. All those fun things, right? Cause constant acceleration, always in the downward direction, blah, 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 blah. Okay? But, need a little more room. But, in this section, now we take that demonstration of just throwing the ball up in the air and catching it, and now I do it like this. Okay? That now I take this ball, I throw it up, and I catch it as I'm walking across the front of the room. To me, like we talked about on Friday, how we describe that motion really depends on where we look at it from. To me, it leaves my hand and it comes back down right in my hand. And that's the case whether I'm standing still or whether I'm walking along the front of the room like this. But if I ask you guys, if I do this demonstration here standing in front of Grace's desk, right, it goes up, it comes back down, same spot, right? But if I'm walking, when I throw the ball, if it leaves my hand when I'm passing Grace's desk, right, I don't catch it again until over here, right? That if we asked you guys to represent that motion, you would have to look at it as some kind of an arc. But for me, straight up and straight down.
When you're walking next to you,
Yep.
when you're throwing the ball up, like you know how it's supposed to be like a curve like this?
Yes.
Kind of, but I see the ball going straight up and straight down. Is that just because you're walking next to it, so it looks like it's just going up and down?
If you just looked at the ball,
Yeah.
right? Okay, so I'm going to take it, and I'm going to throw it, right, when I pass Grace's desk.
Yeah.
Okay? So if I throw it like this, right, I don't catch it until over here.
Yeah.
Even though, yes, I'm walking with it, but if I asked you to draw the path of the ball, right, it starts here and it ends here,
Yeah.
right? You don't see it go straight up and down. You actually see it go in that curved path. Even though because of the context of me walking as well, the illusion exists that, oh, it just went straight up and down. But if you really looked at where it was, right, it started at Grace's desk and now it's over here. But for me, right, to me, it starts at my hand and it ends at my hand, right?
Yeah.
So I could say to me, oh, it went straight up and straight back down. Left my hand, came back to my hand, right? But for you guys, because we have different frames of reference, how we represent that motion is different. Kind of like on Friday when we talked about the person walking on the train, right? That if you're standing on the side, not moving with the train, you have to take into account that person's motion, but also the motion of the train. But if you're watching it from the train, you don't have to take into account the train's motion because you're both moving with that train. Does that make sense?
Yeah.
So it's the same motion, but just represented differently because of where we observe it from. Okay? So, to take that, right, using this picture, girl on rollerblades, has this ball in her hand, she drops the ball. Same idea. If she watches it, it would hit the ground right next to her foot where she dropped it from, straight down. But if we're watching it from the side, we would take it, or we would observe it moving along this curved path. Because one of the key ideas in dealing with motion in 2 dimensions is that there are 2 things going on. There is a horizontal motion, but there is also a vertical motion. And those 2 things are independent of one another. They are occurring simultaneously. This ball is moving both horizontally and vertically as I throw it into the air while I'm walking along the front of the room. But the two motions are independent of one another. Like it says up at the top, independence of motion. It's a key idea when we're looking to analyze two-dimensional motion. The fact that it can be doing two things at the same time, and those two things are independent of one another. They occur simultaneously. They occur at the same time, but they are completely independent of one another. One does not affect the other one. Case in point to illustrate that idea. This demonstration of me throwing the ball up in the air and catching it as I walk across the front of the room. I can do that same demonstration if I'm riding in a car, right? If I'm riding in the passenger seat of the car, not while I'm driving, right? But if I'm riding in the passenger seat of the car, I take the ball, I throw it up, I catch it, right? But I'm also moving horizontally at the same time, the same as the ball. If we ask somebody on the side of the road what the ball did, they would give me a curved path. Right? Third example, I do the same demonstration if I'm riding on an airplane. Okay? Sitting in the seat of the airplane, throw the ball up, comes back down, lands in my hand. Because regardless of the fact that all of those motions, whether I'm walking across the front of the room, or riding in a car, or riding in an airplane, the horizontal aspect of that motion is different each time, but that doesn't matter because the horizontal aspect doesn't affect what happens up and down. Okay? Good there? All right, let's talk about this a little bit more. This idea that this object, the ball in this girl's hand, the baseball in my hand, whether it's walking across the front of the room, riding in a car, riding in an airplane, doesn't matter. This combination of the horizontal and the vertical motion occurring simultaneously, we then refer to making this object a projectile. A projectile is an object that is launched and then allowed to follow a path determined solely by the influence of gravity. Once this ball, write this, then we'll talk. If you choose to write these things down. Projectile is an object that is launched and then allowed to follow a path determined solely by the influence of gravity. So to make that point, in the last chapter, we talked about the idea that I can throw this ball up in the air and gravity affects its motion, right? Gravity slows it down on the way up, speeds it up on the way back down. Once it leaves my hand, gravity is the only thing affecting the motion, right? And that's the case whether I throw it up in the air and it comes back down, or whether I throw it downward. Right? We talked about the idea, especially on the test, that the fact that once it leaves my hand, regardless of whether it's going up or whether it's going down, gravity is the only thing affecting its motion. It causes a constant acceleration, blah, 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 blah. Okay? That's the case here, whether I throw it straight up or straight down or sideways. Once it leaves my hand, gravity is the only thing affecting the motion of that object. But it's not just moving up or down. That effects of gravity vertically, instead of just traveling in a straight line up and down, now we have to take into account that horizontal part, and now we get ourselves a curved path, specifically a parabola. Because, as we discussed in the last chapter, gravity is nice and symmetrical, right? It does the same thing on the way up as it does on the way down. That's why when I throw this object upwards, by the time it gets back to my hand, it's going just as fast, but in the opposite direction. That's going to be the case as well, as long as we can ignore air resistance. It's moving sideways and up and down, but that doesn't change the fact that gravity is the only thing affecting its motion.
I have a question.
Good.
When you're walking by a graze, in order for, if you're walking, for it to go straight up and then back down towards graze, you actually have to throw it behind you.
Yes. But then that also, too, affects what it was doing initially when it came under the influence of gravity's effect.
Yeah.
That I can move it so that when I throw it, it lands behind me like that.
Yeah.
But because that was when it came under gravity's effect, it was moving backwards because of the way I threw it, regardless of the fact that I was walking forward.
Yeah.
Does that make sense?
Yeah.
Right? So yeah, but the main point here being that when we're talking about a projectile, gravity is still the only thing affecting its motion, regardless of the fact that it's now also moving horizontally as well. Okay? And that the combined effect of those two gives us this curved path, or this parabolic path. So a projectile is an object that is under the influence solely of gravity, but that doesn't mean it's just moving up or down. It's moving both horizontally and vertically at the same time, but gravity is the only effect on it. Okay, good there? To further illustrate that idea, another demonstration. So, over here on the side, I have this stand clamp to the table. There's a platform up here on the top. The platform up at the top also has a spring-loaded post, for lack of a better description. And I can pull the spring back, and I flip the switch. That's not supposed to happen, but tighten it up a little bit. But the spring shoots the post out in this direction. Okay? So to start, kind of like a pinball, yeah. To start, notice over here, there's a side of the post that's hanging off the edge. I have a marble with the middle drilled out of it. Okay? So I can hang the marble right on the edge of the post just like that. Okay? When I flip the switch, the post shoots out horizontally this way, but now there won't be anything holding the marble up. So what's the marble going to do? It's going to fall straight down, right? Okay. And then we can use kinematic equations to figure out how long it would take, or how fast it was going when it got to the floor, all those fun things we did back in chapter 3. Okay? But to add to this demonstration, so we'll put the marble at the end. We'll put a second marble though, okay? But I'm going to put the second marble over here on the edge of the platform. So when I flip the switch, the post is going to come through and it's going to shoot the marble sideways. But once it leaves the edge of the platform, what's the only thing affecting its motion? Gravity. So gravity is going to pull it which way? Down. But because of also going to be doing?
Forward.
It's going to be moving forward. So now it's moving forward and down, and it's going to go in a curved path. But the fact that it's going forward while it's going downward doesn't affect what happens to one versus the other one. Okay? So when I flip the switch, we should notice what about when they hit the ground?
Same time.
They should hit the ground at the same time. Because if I take these two objects, right, and drop them from the same height, they hit the ground at the same time, because gravity accelerates all objects the same. The fact that we add a horizontal part to one of the motions doesn't change what gravity does to it vertically. Okay? So, ready? So by adding the horizontal component to that motion, that doesn't change what gravity does to it vertically. Because we can think of projectile motion as free fall, but with initial horizontal velocity. That picture that's on the right-hand side, that's going to be the picture that's on the next 4 slides. So if you want to like draw a little sketch of it, you can just write the stuff next to it because the same picture shows up. Becky, go ahead.
Doesn't that work too? My brother told me that if you take a gun and like you hold a bullet, and like if you drop the bullet and fire the gun at the exact same time, they hit the ground at the same time.
So that's one of the things that goes along with this, because here, let's illustrate that point.
That was on Mythbusters.
It was on Mythbusters.
Was it?
Yeah.
I didn't know so.
So
Eventually
this,
hit the exact-
so Bechtel, this demonstration has 2 settings. Okay, it has like semi-strength and then super strength. Okay, so this one I have it set now on the semi-strength one. Okay, so go here, right? So semi-strength. Okay, and then if I set it to super strength setting.
It's gonna kill you.
The original demonstration I did was actually on super strength setting. So, alright, I go here and set it on super strength, right? Okay. Where does it land?
Further out.
It lands farther out, but does that change when it lands? No, because how fast I shoot it horizontally has no effect on what gravity does to it vertically. Okay? So,
No. What if that was like tilted down a little?
now that's different, because now it's a different height that gravity is affecting it. You know what I'm saying? Like if the platform was tilted, gravity would have it's a smaller distance that gravity is acting on the side that's tilted down versus up. Does that make sense? Okay? And if I shot it at like an angle, right? Now the one I shot at the angle, it would have to go up and down, whereas this one just has to go straight down. So that doesn't work because that's not the same vertical setup, right? But if we have the same vertical setup, like shooting a bullet and dropping a bullet, they will hit the ground at the same time because vertically they're being affected the same way by gravity. Okay? Now another thing that plays into this is if I do this. Okay? So if I tilt the apparatus, I set this one up here, and I set this one up here,
Wait, you tilted it?
I don't like that.
I twisted it.
Oh,
Okay? So now there's no way it's going that far.
is that?
So I
Well, I
tilted
just
it,
gonna go like far
right?
back.
Super.
And if I do this, right? Okay,
No bullet.
Bye-bye.
they didn't hit the ground at the same time, right?
Right.
But why?
But that's stable.
Because the ground wasn't in the same spot, you know? So in that case again, we have messed around with the vertical aspect of its motion. But if we kept the vertical aspect exactly the same, it doesn't matter how fast we shoot. Okay?
So,
Because the horizontal motion doesn't affect what's happening to gravity vertically. Does that make sense? Yeah. And like I said, Mythbusters did that, and they showed it works. So within like millionths of a second.
And they like gosh where that bull can land, so they actually hit each other.
Yeah. So yeah, they originally put out like they just fired a gun to figure out where it lands, and then they basically set up an apparatus just like this, and
so it would drop it and
Yep.
they hit each other?
yeah. So maybe if we have some time next week, we can watch that clip. So it's like they do like a little summary. It's like 3 minutes long, So, but the horizontal motion does not affect the vertical motion. They occur simultaneously, but they are independent of one another. That means they occur simultaneously, but they are independent of one another, meaning that gravity affects both of them vertically, and gravity causes, right, that acceleration of 9.81 meters per second squared. And we can see that on the red one, right? The red one is definitely accelerating. How can we tell that it's accelerating?
There's a little, there's more space.
The spaces keep getting bigger and bigger and bigger, right? The yellow one is accelerating as well. And we can tell that because if we look at the white lines for reference, what do you see about where the red one is and where the yellow one is in relation to all those white lines? At least from a height standpoint. They keep hitting the white line at the same time, right? Or close to it. Because they're both being affected vertically by gravity, even though the yellow one is moving horizontally as well. But, like we discussed, once it leaves the platform and the post shoots it forward, there is nothing affecting the horizontal motion. So acceleration in the horizontal direction is equal to 0. If acceleration is equal to 0, what happens horizontally?
Just dropping straight.
Well, that's what happens to it vertically, right? Horizontally,
It's
what?
not moving left and right.
Not that it's not moving. It's not what?
The same.
It's not changing, right? It continues to move horizontally even as gravity affects it vertically, which is why when I'm walking, right, I can throw it up and catch it in the same spot because the ball continues to move horizontally even though gravity is now affecting it up and down. Okay? Back to go ahead.
Well, but isn't it, like, say you were to fire a gun,
Yep.
and it's like a 400 FPS, like 400 feet per second,
Okay.
right? So you fire it for the first second, it goes 400 feet, then for the second second, it's slowing down, so it's
Not
accelerating.
horizontally.
That's
Well,
'cause that's
we have to make
moving,
one big assumption here, right? What is the one big assumption we have to make?
the air resistance.
Air resistance, right? So that's, that's the big assumption that we have to make, right? Okay. Go ahead.
Okay, so you know how the Earth is always moving?
Yeah.
So, you know how, like, let's just say it's moving 300 miles per hour. I know it's not, but let's
Faster
just,
than that.
yeah,
Okay,
yeah, but like, so when you take a rocket and you go up, it's technically moving horizontally 300 miles per hour. let's
Correct.
say. So then when they land on the moon is not going 300 miles per hour.
Correct.
So shouldn't there, like, something happen, like, they just smack, I don't,
Well, they adjust that, right? So I could take this, okay? Think about it, if we think about it in terms of that, like a football game, right? So let's say a quarterback is running as he throws the ball, okay? There's a horizontal motion there that the ball already has. Now it goes up and down, right?
yeah.
the receiver isn't necessarily running the same speed that the quarterback was running. You know what I'm saying?
Yeah.
Okay? So the receiver on the receiving end can adjust his horizontal speed so that they end up meeting in the same spot, which is kind of the thing. Like, you know, once the spaceship blasts off, right? Yes, it's moving horizontally, but it can, based on the rockets, like the thrusters and stuff that are on that ship, it can adjust how fast and how far it's going, not as dramatically as it does at liftoff, but it does adjust its speed and its direction.
Okay.
You ever see Apollo 13?
Yeah.
Okay. Do you know there's that one part where they have to like fire the rockets when they're watching the moon through the window?
Mhm.
You know what I'm talking
Yeah.
about? They're changing their trajectory because of this idea that if they didn't do anything, it would just continue moving like it's currently moving. But they can change what they're doing both horizontally and vertically by adding another effect.
Yeah.
It's another force, which we'll talk about forces in the next chapter. But if gravity is the only thing acting on it, horizontally it just keeps doing the same thing. You know what I'm saying?
Yeah.
Yep. All right. Are we good there? Okay. So, to wrap this up, in the last chapter, hold on, don't write the whole thing. I'll tell you the important part. In the last chapter, we introduced these equations down at the bottom to represent the position of an accelerating object. Those equations down at the bottom will hold true for an object that is moving in 2 dimensions. It's just that we need 2 equations, one to represent the horizontal motion and one to represent the vertical motion. That's why one of them is x and one of them is y. Right? Because one of them represents the horizontal part, one of them represents the vertical part. Okay? But those equations representing the position of an accelerating object at a specific time can be used to describe an object moving in 2 dimensions, a projectile. But you need to have 2 equations because there are 2 motions. There's a horizontal motion and a vertical motion. And therefore, you got to represent both of them separately. Tomorrow, we will see how we take these equations and tailor them to specifically fit what's happening horizontally and what's happening vertically so that we can mathematically represent those 2 dimensions. Okay?